Good morning, everyone. We are here to present our project titled Automated Washing Machine Control System, developed during our embedded system internship. This project is a collaborative effort by me, Akanksha, and my teammate Vikash. The entire internship was conducted under the guidance and sponsorship of EMERTXE, a reputed institute in embedded system training. I will be taking you through the programming foundation, logical construct, and system objective that form the core of our project, while Vikash will cover the rest of the implementation and outcomes. Let's begin with the heart of the embedded development, C programming. C, developed by Dennis Ritchie in early 1970s, is still one of the most powerful and efficient programming languages used in embedded systems. Here is why. It is a procedure making code structured and easier to debug. It gives low-level access to memory and hardware, which is critical for working directly with microcontroller registers. Its efficiency ensures optimal performance in time and memory constrained systems. And finally, it's portable, allowing the same code to be used across various platforms while little changes. These features made the C perfect choice for our programming washing machine control system as it had to interact with hardware components like sensors, motors, and buzzers. So let's move to our next slide. Basic data type in C. Now let's look at the basic data type in C, which are fundamental to any C program. In embedded systems, selecting the right data type is extremely important, especially because memory and processing power are limited. Here are the main types. Int, used for storing whole numbers like counts, flag, or stay values. Float, used for decimal values. Double, similar to float but with more precision, used when calculation requires accuracy. Char, stores single characters like mode indicators or status symbol. In our project, we used int for step control and water levels. Char were used for mode selection and float helped manage time-based delays more accurately. Choosing the right type ensured our system was more efficient both in speed and memory. So now let's move to our next slide. Conditional construct. Now let's go deeper into one of the most important concepts in C programming, conditional construct. These allow us to create intelligent behavior in an embedded system by letting the code make decisions. There are usually three types. First one is single iteration, decision making statement. These include if else, switch case. They help the program take a decision based on real time condition. This type of logic was used in our washing machine to control water flow based on the sensor feedback. The switch case statement allowed us to define different wash modes like normal, quick, and heavy and execute different code blocks for each. And the second one is multiple iteration loops. These include while continues as long as condition is true, do while runs at least once before checking, for used for fixed repetition. In our project, we used a for loop to trigger an alert. This looping helped automate repetitive tasks like spinning or draining cycles. And the last one, unconditional construct, control flow. These include break, used to exit loop or switch block, continue, skip current iteration, and continue the loop. This logic ensures emergency stop functionality, allowing the machine to halt operations immediately, an important safety feature. So, in summary, Conditional construct allowed our microcontroller to react to sensor data, make decisions based on user input, and control timing and safety in real time. These constructs transformed our code into a smart machine controller. And now let's move to the next slide, the embedded system. Now, what exactly are embedded systems? An embedded system is a dedicated computer system designed to perform one specific task, unlike a desktop or smartphone that handles many applications. It's a combination of hardware like microcontrollers, sensors, and actuators, and software, program logic written in C or assembly language. The example of this includes microwave ovens, pacemakers, smartwatches, washing machines, etc. They come in many types: standalone systems such as calculators, real time systems where the timing is critical, like ABS in vehicles, network embedded systems like home automation using IoT, mobile embedded systems like wearable fitness tracker. Core components of any embedded system contains a processor or CPU, RAM or ROM, IO ports, communication modules, and power supply. In our case, the PIC16F771 microcontroller served as the CPU. We interfaced it with water level sensor, a buzzer for alert, and relays to control the motor and valve. So our embedded system was a perfect blend of hardware control and software intelligence. Let's move to our last slide. Our project objective. The main aim of our project was to automate the functionality of a washing machine using a microcontroller, making it more efficient, safe, and user friendly. Here is what our system does. It detects water level using sensor, controls the motor for washing, rinsing, and spinning, triggers a beep when the cycle is complete, all while requiring minimal user input. Why does matter? Convenience, no manual intervention once started. Energy and water efficiency, sensor avoid overuse. Safety, emergency stop and checks built in. We choose the PIC section F77A microcontroller due to its multiple I/O pins, timers, analog to digital converters, EEPROM storage, all essentials for controlling multiple hardware components in real time. And all the logic, as mentioned before, was written in embedded C using the construct we discussed earlier. This project gave us a real world experience in microcontroller programming, hardware software interfacing, and automation logic, which are all key skills in the C domain. So that concludes my part of the presentation. I hope I was able to give you a clear understanding of how we build the foundation of this embedded system using C programming and logical instruct. And now Vikash who will take you through the next phase covering our development tools, project methodology, implementation and results. Thank you.
Now let's move on to the topic tools used. There are mainly three components used in this project. That is MPLAB IDE. It is a program-based application which uses X8 compiler and a PICSIM simulator where we are going to work upon PIC board using PIC16F77A microcontroller. Also some peripherals like LED, digital keypad, CLCD, fan and a buzzer. Now let's know more about MPLAB IDE. MPLAB IDE is a free development environment created by Microchip Technology for designing and programming PIC microcontrollers. It is based on the NetBeans platform and supports tasks like editing, debugging, programming for 8-bit, 16-bit, 32-bit microcontrollers. It uses compilers like MPLAB X8 for programming and supports languages like C, C++, and assembly. Now let's know what is a PICSIMLab. PICSIMLab is a graphical simulator used to test PIC microcontrollers, and it uses projects without a physical hardware. It supports PIC16F and PIC18F families, works with SDCC and LabXE8, and includes a virtual interface with components like LEDs, switches, and motors. It allows uploading of hex files for testing and runs over Windows, Linux, and Raspberry Pi, and also supports real-time simulation, making it useful for debugging and cost-effective prototyping. Simply, it is a graphical simulator without a physical hardware. Moving towards the interface of PICSIMLab on PICGenius board and using a microcontroller PIC16F77A. This is the interface of the PICGenius board and PIC16F877A microcontroller. Now let's know about architecture of PIC16F877A. Before knowing the architecture, let's know what is a microcontroller is. A microcontroller is an integrated circuit designed to perform specific tasks in an embedded system. It is a compact computer that includes processor, memory, input-output ports on a single chip. In this project, we have used PIC16F877A microcontroller. Now let's know about specifications of PIC microcontroller. PIC stands for Peripheral Interface Controller. It is very easy to use flash memory technology so that we can rewrite and erase it thousands of times. It supports several communications for as it has two pins like TX and RX. It can also support SPI protocol. This is the architecture of PIC16F77A. PIC16F77A supports three timers. Timer 0, it is of 8 bit. Timer 1, it is of 16 bit. Timer 2, it is of 8 bit. And PIC16F77A has 5 ports: Port A, Port B, Port C, Port D, Port E. Port A of 6 pins, Port B of 8 pins, Port C as well as 8 pins, Port D of 8 pins, Port E of 3 pins. This is the block diagram of PIC16F877A microcontroller. Now let's move on to the CPU. CPU is one of the most important part of PIC16F877A architecture. The CPU consists of an arithmetic logic unit ALU and a memory unit MU, a control unit CU, and a accumulator. ALU performs arithmetic and logical operations, whereas MU stores instructions to be processed and data after processing. The analog to digital converter in PIC16F77A is controlled by a special register named ADC0N0, ADC-C0N1. The resolution of A to D converter is in peak is 10 bit and with sampling rate up to 100k samples per second. The signal can vary from 0 to 5 volts. Peak 16F887 has program flash of 8k bytes, data memory of 368 bytes, data EPROM of 256 bytes. Now let's know about the interrupts. An interrupt is a common communication process set up in a microprocessor or a microcontroller in which an internal or external device requests to the microcontroller to stop the processing. The microcontroller acknowledges the request, attends the request, goes back to the processing where it was interrupted. In PIC16F87 architecture, it consists of 20 internal interrupts and 3 external interrupts, which are associated with different peripherals like ADC, USART, timers, and so on. Now let's know about peripherals. There are many peripherals. One is LED. LED is a semiconductor device that emits light from an electric current when it passes through it. Uses of LED. It is used in indicator lights, display panels, automotive headlights, remote controls. CLCD. CLCD stands for character LCD. It refers to the type of liquid crystal display. It is commonly used to display character and symbols. Character LCDs consist of grid pixels arranged in row and column. Each pixel can turn on and turn off, allowing it to display specific character or symbol. They come in different size, and these are used for pro- communication protocol such as in 2C and SPA protocol. Tactile switches. Tactile switches are small, momentary push button switches that provide a physical feedback on a click feel when pressed. They are used to complete or interrupt an electric circuit. Uses of tactile switches. Used in keyboards, keypads, remote controllers, consumer electronics, embedded system input panels. A fan. A fan is an electrical device that creates airflow by rotating blades used to circulate air or provide cooling. Uses of fan. Cooling rooms, personal space, ventilation in buildings and vehicles, cooling electronic devices and machines. A buzzer. A buzzer is an audio signaling device that provides a beeping or buzzing sound when powered on. It can be mechanical or electromechanical or piezoelectrical. Uses of buzzer. Alarms, warning systems, used in timers, notification alerts, and electronic toys and games, etc. Now let us know about timers. Timers in microcontrollers are versatile hardware modules used for measuring timetable intervals, generating precise timing signals, and implementing time-critical operators. PIC16F877 has three independent timers: Timer 0, Timer 1, and Timer 2. Timer 0 is an 8-bit timer with 8-bit prescaler. Timer 1 is a versatile 16-bit timer with prescaler and a post-scaler. It is used to generate PWM signals. Timer 2 is an 8-bit timer with prescaler and a post-scaler. It is used for fixed frequency PWM signals. Moving forward to the most essential part of our project. Now let's know about power on screen description. As soon as the board gets reset, it should show press key 5 to power on washing machine on the CLCD screen. After switch 5 is pressed, it should print powering on washing machine on the CLCD screen. Let me show you on the PICSIMLAB simulator how it works. So this is the interface of PICSIMLAB upon PICGenius board and using PIC16F877A microcontroller. After clicking on reset button, it should show press key 5 to power on washing machine. And we have coded as RB4 as switch 5. And as I said in before slide, that after pressing on switch 5, it should show powering on washing machine. And it should go on washing machine program screen. So as it is working fine and it has shown powering on washing machine and it has moved to washing machine program. Now moving on washing program screen. The washing program screen menu will contain the following washing options like daily, heavy, delicates, etc. Using the keypad switch 4, we can scroll between the options available. A long press of switch 4 will select the option which is highlighted with a star mark. After this completion, the washing program screen will move to water level screen. This is the washing programming screen with some options like daily, heavy, delicates. If I want to choose any other option, I can click on switch 4 to scroll up the options. Here you can see. And if I need to select any one of them, then I need to long press on switch 4. then it will go to water level screen. Moving forward, water level screen description. The screen allows the user to select the water level. The water level menu will continue the following displays: auto, low, medium. Using the keypad switch 4, we can scroll between the available options. A long press on switch 4 will select the highlighted option which is marked with a star. After completion of water level screen, it will go to start screen description. Once washing program and water level are selected, provide user option to start the machine. If switch 5 is pressed, the machine starts and display the function selected and time taken. Then it switch to the function screen. If not, switch 6 is pressed, it will go back to the washing program screen. Let us assume we have pressed switch 5 and the function screen arrived. Once the machine starts, it will display the function going on like wash, rinse and spin, and display the time in the left side of the CLCD. If switch 5 is pressed, the machine starts, and if switch 6 is pressed, the machine pauses. Even if the start command works, we can pause in between. In case we press switch 1, it is the door status actually. If switch 1 is pressed, the door is open. If switch 1 is not pressed, the door is closed. If switch 1 is pressed, it also indicates that turn on buzzer and display. It will simply turn on buzzer and display, and at last it will show door open and door please close tabs. Completion status screen description. Once all programs are completed, display notification will be shown. Program completed, remove clothes on CLCD. Let's recap everything from the beginning. Before going to begin, let me restart everything. After clicking on the restart button, the CLCD display will show press key 5 to power on the washing machine. Here key 5 is RB4. After clicking on RB4, which is switch 5, it will show an interface where it would be written as powering on washing machine, and it will directly go to washing machine program, and it has some options like daily heavy dedicates. If I want to select any other options or I want to scroll up, I can click on switch for that is RB3 here. You can see it scrolled up, and if I want to select or go with heavy, then I need to long press on switch for first 10 seconds maybe. If I keep pressing on switch for, it will directly go to water level screen. In water level screen also there are some options like auto, low, medium. If I want to go with any other option, same as previous process, I can scroll by clicking on RB3. If I want to go with auto, I can long press on switch for, and I'm going with auto, and I have clicked RB3 for a long time. So the now interface changed and it came to start screen. Here there are two options: switch 5, switch 6. Switch 5 to start, switch 6 to stop. In switch 6, if we press switch 6, it will go back to the washing program screen. If we press switch 5, it will start and it will take to function screen. Let me show you this. And it will also show the program like what I have selected, heavy and its timing. Now it has come to function, and the option is wash, and it also showing the timer. If I will press on start, it will start the timer, and if I will pause, it will pause the timer. Let me show. If I click on switch 6, it will pause. If I will click on switch 5, it will start again. See, it is working again. And if I click on switch 5, it again got stuck. If I press on switch 1, and let me start here also. If I press switch 1, it will turn on buzzer and fan. And when the program is completed, it will show program completed and remove clothes. Now let's know about the conclusion. This project created a smart washing machine simulation using the PIC16F877A microcontroller, which includes components like timer 2, interrupts, push buttons, and etc. Also a 16x2 LCD display. All these help to turn a simple hardware into an intelligent system that could wash, range, and spin automatically without any human help. Beyond just building a simulation, the project showed how microcontrollers can automate real world tasks. It proved our technical skills and gave a preview of future smart systems where machines can think and act on their own.